All right, we should look at a little thing called improper integrals. We have definite integrals, indefinite integrals. Now we have improper integrals. What we've been doing are proper integrals. These are going to be improper. Here's why. To look at a couple here, notice something different about this one. Here we're looking at the integral 1 to infinity of 1 over x squared dx. Of course, you can see there a little something different than we've ever had, and that is we have one of our limits being infinity. It's called an improper integral. The other one is, it has the infinite nature feel to it as well, but in a little different way. This one's going to have 0 to 2 limits. But one thing we haven't done is, notice here, we have incorporated a little something in this that we haven't done before. Do you notice here something about 0 to 2? In 0 to 2, I have a little bit of a problem because at 1, the function is not defined, is it? So I've captured the undefined here. You know, if it was 2 to 3, this would be no problem. We just do, you know, our regular old run-of-the-mill thing. But the limits here include x equals 1, and the function is not defined at x equals 1. And it kind of goes hand in hand with this because this is also kind of an infinite, including some infinity here, because think about the graph. The graph of this looks like something like this, I think. Those at x equals 1, we've got our little asymptote thing, don't we? So our function on either side of that is going to infinity. Hence, we are including an infinity scenario here. It's just in a little different way. So that's an improper integral too. If you've got call it discontinuity, non-removable, but if you include a discontinuity in your integral, or if you have an infinite limit, or both of them are infinite limits, those are called improper integrals. Those two types. Okay? And we'll look at both types here in a moment. Okay, so what does this mean? Let's start with the first type here, where one of our limits, one or both limits, are infinity. Let's look at that type of limit first. Okay, what does that mean? Well, this is meaning we're going to let the upper limit go out to infinity. Not just stopping at 10 or 100 or 1,000. We're going to run 1 out infinitely. Well, one thing we can do here, because this is not a terribly difficult antiderivative, is let's just think about progressively doing that. Let's choose our limits here. Let's do, say, 1 to 5 of 1 over x squared dx. So our first upper limit is 5. Well, what is that derivative there? Since that's x to the minus 2, the antiderivative would be what? Minus 1 x to the minus 1. 1 to 5, and that, if you notice, will be negative 1. 5 to the negative 1 be negative 1/5. 1 to the negative 1 be negative 1 over 1. So you get 1/5 plus 1, which is negative 1/5 plus 1, which is 4/5. Okay, keep that in mind. All right, let's do something a little further out for our upper limit. We could go 1 let me do the ones I did, and I'll cut to the chase here. 1 to 10. 1 over x squared dx. So we get a little further out. Not quite to infinity there yet, but go a little further out. And so that's the integral 1 to 10, x to negative 2. So that would be, let's just go right here. That would be negative x to minus 1 from 1 to 10, which is negative 1/10 minus a negative 1 over 1. So that's negative 1/10 plus 1. That's 9/10. I think I'm pretty well on the screen there. Almost. 9/10. All right, well, a little better. How about we go out 1 to 100 of 1 over x squared dx? Talking about running our limits, one of our limits to infinity. So let's run the top limit to 100. So that would be negative x, negative 1 of 1 to 100. Well, that would be negative 100 minus a negative 1 again. What is that? That would be 99 over 100. Well, I think we could see 1 to 1,000, we'd probably get what? 999 over 1,000. These, what do these seem to be going to? Don't those seem to be going to 1? If I run, we're talking about doing a upper limit of infinity. So, if I look at 1 to 5, I get 4/5. If I look at 1 to 10, I get 9/10. If I go 1 to 100, I get 99 over 100. Don't these right here seem to be going to 1? Does seem to. Turns out, it does go to 1. There's actually a limit here. If you think about it, that's kind of remarkable that I'm running, here's my, my graph would look like this on this side. So I'm going 1 out infinitely. So I'm getting all that, however far you want to take that. From here out to there, it seems to be that the total area that has is 1. I mean, it's sort of makes sense because this is getting very, very close to the x-axis. But anyway, we can prove this. We don't have to. This is kind of the table sort of thing that we were doing way back in the day. First thing we did in calculus, but just about the first thing. But we can actually do this with limits. I can show you with limits this does equal, it turns out to be 1. Okay? But that's the idea. Okay? Using this limiting process. All right? All right. So let's do this the more direct way. Seems to be what it's doing. Let's see about it. A direct way, mathematically speaking. Okay? All right, so let's go back to our same 1 to infinity, 1 over x squared dx. Here's what I'm going to do. I'm going to get rid of that infinity for the time being. And I'm going to kind of do a t substitution, if you will. I'm going to let t run to infinity. So I'm going to put a limit, t goes to infinity, 1 to t, 1 over x squared dx. Okay? That kind of is what we're doing, right? I'm going 1 to infinity, but if I set it up, just do it as an integral, 1 to t, see what that gives me, and then do a limit of that. Same idea, right? Okay, well, we've already done, so it would be the limit as t goes to infinity. It would be x to minus 2, so that's, we did that earlier, didn't we? Minus, was it minus x minus 1? So I'm going to go that 1 to t. Plug in the t, so I get the limit, t goes to infinity, of, it would be minus t to the minus 1, minus a minus 1 to the minus 1. So that's limit t goes to infinity. Let's put it in this terms. That would be minus 1 over t, wouldn't it? And that is plus 1, 1. Okay? Well, once we get it completed, the integral, now we can do the limit. Now let's do the limit of this. Going back to our limit stuff. One of the reasons we talked about limits, it happens to come up ever so often. Okay? What is the limit of this? Can we say? Well, obviously the limit of that is 1. As t goes to infinity. Doesn't matter what t goes to. That's still going to be 1. What about this? As t goes to infinity, that goes to 0. Doesn't it? You've got negative 1 over infinity. Negative 1 by a larger and larger number. That's going to 0 by limit. 0 plus 1 is 1. Okay? So this integral, here's your proof there, if you will, that integral is 1. The area, so the area under the curve, this 1 over x squared, out to infinity, however far you want to draw it out there, that area under that curve just adds up to be 1. Turns out to be 1. Geometric perspective. Okay? So that, I mean, this doesn't stop, but it turns out, area-wise, the area under that curve is all the way out there. Just adds up to be 1. All right? Let's try another one. This way? From, with respect to y? No. No, that's, I mean, you can do the same thing with it, but it might, we'll run into, it won't always be a whole number. It might be infinity. Just depends on the function. We'll run into some of that, but let's try another one. All right, so let's go 1 to infinity again. X e to the minus x squared dx. Let's try that integral. I call it, I don't know if the book calls it this, but let's do our t limit thing. Do the limit as t goes to infinity. Integral 1 to t x to the e to the minus x squared dx. And then it's just, starting off anyway, just a regular old do your integral. How would I do that integral? Because you could do anything as possible. Parts, use substitution, could have the inverse trig function. Could be anything. What about this one? Always try first, use substitution. Will use substitution work here? You see that? Because if I do u equals what? Negative x squared. Then du is negative 2x dx. Got the minus 2x there. Yeah, isn't that x going to cancel with that x? That's what's telling me u substitution is going to be a good option here. So that'll be the limit as t goes to infinity. Integral 1 to t for x, but so it'll be x e to the u du over minus 2x. The x's cancel, so it's just the integral limit t goes to infinity of the integral e to the u minus a half e to the u du. So now that's just a e power antiderivative. What's the antiderivative of e to the u? E to the u. So the antiderivative here is minus a half. Antiderivative of e to the u is e to the u. But u is, what was u? Negative x squared. And I'm going to run that from 1 to t. Is this okay? All right. that's the limit as t goes to infinity. Now plug in your limits. That would be what? Minus a half e to the minus t squared minus negative a half e to the negative 1 squared, which is negative 1. Now sometimes putting it in a little different format may help you decide what your limit is. That would be, wouldn't this be similar, I could write this as 2e to the t squared. Just flip this this part of it, flip it over. Make it 1 over 2e to the t squared. This is plus, let's just write it plus 1. Do the same thing here. Be plus 1 over 2e. With me on that? Now what? Now we do our limit. T goes to infinity. If t goes to infinity, what does this thing go to? That also goes to 0, doesn't it? Because that's going to infinity squared, and you got e to the infinity squared, that's going to infinity. So I've got, and then 2 times infinity is infinity. So I've got negative 1 divided by infinity. That's 0. What does this go as t goes to infinity? 1 over 2e. Okay, so this limit is 1 over 2e. Probably not what you guess when you look at that. That's what you get. So this integral, 1 over 2e, which is not not a very big number, is it's 1 divided by, what is e, 2.72 about. So that's basically 1 divided by 5 point something, yeah. About a fifth. Okay. Not much area there, but it is the area. Area under the curve. 1 to infinity. Okay? Okay, yeah, so let me do this one. A much easier antiderivatives. 2 to infinity, 1 over x dx. It really wouldn't matter if it was 1 there or not, but yeah, I have a reason for doing 2. Okay. All right, so 2 to infinity. So, improper integral, we set our infinite thing. So we set that equal to t, or let t go to infinity. So it'll be 2 to t, 1 over x dx. Well, this is an even easier antiderivative, but I wanted to make a point about this one, because this can happen too. What happens there? What's the antiderivative? Well, that's just the antiderivative of 1 over x, which is natural log of x. So I have the limit as t goes to infinity, natural log of absolute value of x. And I want to go that 2 to t. Do our limits. So that'd be the limit as t goes to infinity, natural log of absolute value of t minus natural log absolute value of 2, which is 2. And matter of fact, t is positive here, so it'd just be natural log of t. It doesn't really matter if we notice that or not. But now we're ready to do our limit. Natural log of t minus natural log of 2. What about the limit? Well, for this one, as t goes to infinity, what's the natural log of t go to? Think about the graph, right? Natural log of t, natural log of x. As we go out to infinity, it's not as steep as some things, but it is going up, isn't it? That's also going. Yeah, the natural log of t as t goes to infinity is infinity. This is infinity. What about that? Well, we have infinity minus the natural log of 2, which natural log of 2 is not very big. So if this is going to infinity, that's going to take over, isn't it? This limit is infinity minus a small number, which is still infinity, okay? More or less. So in this case, think about it. We had 1 over, wasn't the first one we did 1 over x squared? It was 1. And the 2 doesn't make it, I mean, 2 over, if we did 2 to infinity, it wouldn't change it that much, probably not very much at all. That was 1. But if I went 1 over x, 2 to infinity, that's infinity. There's not just a whole lot of difference between those two functions, but there's a big difference as far as their areas go, as this shows us. Now, which also brings up another point. If we have one of these improper integrals and it goes to a number, like 1 or 1 over 2e, if we go to a finite number, that's called a convergent integral. We say that the integral converges. If an improper integral has a finite answer, meaning a number answer, the integral converges, or is convergent. Okay? Convergent. Converges to a number. That's the idea. If the improper integral does not converge to a number, goes to infinity, minus infinity, that's divergent. Okay, so we have the integral 2 to infinity 1 over x dx, that equals infinity. Yeah, this integral is called divergent, or it diverges. Okay? And it, like I said, if it goes to negative infinity as well. All right, so let's do one slightly bit different. Is that okay? Question? Any problems think of right now on these? All right, let's say we go the integral minus infinity to 2 e to the x dx. Interesting one here. So what are we going to do here with our t limit? T is going to go to negative infinity, yeah. Sometimes that might make a difference. A lot of times it may not, but it is going to negative infinity here, and I'm going t to 2. So the t is down here, the lower limit, e to the x dx. All right, well, this isn't too bad of an antiderivative. What's the antiderivative of e to the x? E to the x, okay. And I want to go t to 2. And so what do I have then for evaluating the integral? Well, it'll be e squared minus e to the t. Plug in the 2, we got e squared. Plug in the t, we got e to the t. Maybe a little bit trickier here because t is going to negative infinity. Well, the first one's not. What is, as t goes to negative infinity, what does e squared go to? Well, that's just a constant. That's e squared. Now, as t goes to negative infinity, what does e to the t go to? T is going to minus infinity. So, again, you can think of the graph. Think of the graph. Here's e to the t. Do y equals e to the t. E to the t does that, right? I'm going to minus infinity. So what does this go to? It goes to 0. E squared. That's it. So we say convergent or divergent? Because it'll ask you some of those. Is this integral convergent or divergent? Well, if it goes to a number, finite number, e squared is just a finite number. Convergent. Convergent. That's the term. Okay. This next one that I want to do is kind of a weird one, but it involves a function we don't talk about a whole lot. Maybe you talked about it a lot in trig, but probably not even a whole lot then. It's the tan inverse. The inverse trig graphs. Let's do tan inverse. Just talk about it for just a second. What does a graph of that look like? Remember? What I'm interested in is what happens as I go out to infinity and the minus infinity. A couple ways you can do that. If you think about tangent, let's do it this way. I do it different in my notes, but if you think about tangent, what we're looking at, the tan inverse, we have to do a one-to-one type thing. And so the tangent looks like this. This part is what I'm looking at doing the inverse of. And this number here is pi over 2. This is minus pi over 2. Well, the inverse tangent takes that, and if you know anything about inverse functions, it reflects it. Yes, it reflects it. Basically, it takes the x's and turns them into y's, and y's turns them into x's. So these x's, the x is pi over, that becomes y's over here. Well, whoop, positives there, negatives here. You with me? Those then become my asymptotes. And then the rest is, what does this? Something like that. So what, as x approaches infinity, what does tan inverse approach? Pi over 2. As you go out to infinity, tan inverse approaches pi over 2. And as x approaches negative infinity, tan inverse approaches negative pi over 2. Okay. So I wanted to mention that, explain that, so I don't have to explain it during my problem here. But it's a little different, okay? Tan inverse approaches pi over 2, negative pi over 2, depending upon x or negative. Yeah. As you go this way, it's negative pi over 2. As you go this way, it's positive. Okay. All right? Okay. Well, the other thing to mention before I do the next problem is to mention, what if I have an integral f of x dx, and I not only have infinity going there, I also have the old double infinity there. I got minus infinity lower limit, positive infinity upper limit, because why can't I go both ways? Well, a lot of times you can't go both ways because of the way the shaded graph goes, but some graphs we can actually think about doing a negative infinity to positive infinity sort of thing. How do I do that? Well, the way we can approach it using our t limit is we can break it up into two places, because this is saying I'm going to go from negative infinity to positive infinity. I'm going to break it up into two integrals, and then I'm going to break it up at a value, whatever value you want to. Zeros are usually logical choice, isn't it? So I'm going to break up this function into two parts. I'm going to go negative infinity to 0, and then 0 to infinity. The a to c, break it up into the a to b, break it up, we did that sort of thing before, it's just now we're doing with infinity. With me? Why do I choose 0? 0 is just a good one to choose. Could I do it at 1? Sure. Could I do it at 100? Sure. Break it up at 100 if you want to. I'm going to go with 0. All right. So let's try that. On this one. We can use t in both of them. Yeah. We're going to use t in both of them. Yeah, so then we're going to go limit as t goes to negative infinity here. Because it's two different limits. You see what I'm saying? You can just use t in both cases. It'll be fine. All right, here it is. All right, so let's say we've got negative infinity to infinity, 1 over 1 plus x squared dx. The other one? Oh, it is. Okay. So that's where we'd apply our little technique there. So I'm going to go negative infinity to 0, 1 over 1 plus x squared dx. And then plus 0 to infinity, 1 over 1 plus x squared dx. Then I do my t limit thing, limit as t goes to infinity, negative infinity, t to 0. And then this one, the limit, t would go to positive infinity, 0 to t, 1 over 1 plus x squared. Okay, well, that's where I get into what I was talking about. What is the antiderivative of 1 plus 1 over x squared? Anything? It's an easy one. Does it remind you of anything? Tan inverse. Yes, that's tan inverse. Tan inverse of x going from t to 0. So I have the same thing over here. Limit as t goes to infinity, tan inverse 0 to t. All right, well, that's going to be the limit as t goes to negative infinity. A little bit of writing here, but so that's going to be tan inverse of 0 minus tan inverse of t. And about the same thing over here, just flipped around. T goes to infinity. Tan inverse of t minus tan inverse of 0. And it does make a big difference getting those in the proper order. Because here's what happens. Now, we did talk about it a while ago, but what about tan inverse of 0? That's looking for tan inverse of 0 equals what? That's saying the tangent of what is 0, which is what angle, so to speak, what angle gives you tangent to 0? 0, isn't it? Tangent of 0 is 0. So tan inverse of 0 is 0. It's nice, okay? And it doesn't matter, t goes to negative infinity. Now, it does matter here, minus then tan inverse of t, and t is going to negative infinity. That's what we just talked about. As t goes to negative infinity, what does tan inverse go to? Think about the graph here. It was as t goes to negative infinity, it's negative pi divided by 2. Now, notice there, it's minus negative pi. The minus there, and then the tan inverse going to negative pi over 2. Okay? What about here? Well, t goes to infinity, what does tan inverse go to? Well, tan inverse goes to positive pi over 2 in that scenario. Tan of 0 is 0. So what have I got? Well, I've got 2 negatives. I got pi over 2 here, plus pi over 2 there. Pi over 2 plus pi over 2. Fine. Turns out, from negative infinity to positive infinity, 1 over 1 plus x squared is pi. The area under the curve, graphically speaking, here's 1 over 1 plus x squared. Well, it's not quite that tall. The area from negative infinity, went off the board, didn't I? I went too far. All right, so off the screen. All right, and then here goes to there. From here infinity there, negative infinity. It's pi. Pi is the area under that curve. Kind of something to think about, isn't it?